Okay. This is a PDF version, but anyway, it doesn't matter. It does the work for us. So you already have the part of it. So in the initial part, we talked about the static stability part, which is the first essential thing. Now we'll start looking at the dynamic stability. For the term test 2, this presentation and the next one will be included, but it will still largely cover the whatever we have done so far. So parts of it I had tried to cover in the mock test, but we'll see how much we can cover further. So basically the objectives are to derive the equations which control the flight of an aircraft, the aircraft motion equations. That will be the final part. And we'll also try and see how we can use the frequency domain and the state space techniques of handling the equations. Describe the advantages of both techniques. Okay, now the traditional control system people, you must have, I don't know if you have studied part of the control system somewhere, they convert the differential equations using Laplace transforms, right? So when they use Laplace transforms, you get a equation in terms of S, and the roots of that equation will tell you where the system is stable or unstable, and then also you can come up with a feedback system how to make it stable. That's the kind of frequency domain method, but that unfortunately is valid only if the initial differential equation, time differential equation, is linear. Okay, because Laplace transform or Fourier transform or any transform technique works on the assumption there is that principle of superposition. That is, you have different solutions of the problem. You can add all of them to get the final solution. That's called the principle of superposition. That is valid only if the original differential equation is linear. Many times in aircraft dynamics, the equations are non-linear. If they are non-linear, then of course you cannot use the Laplace transformation, and you have to do matrix-based method. So there are two techniques. We'll talk about them. We'll not go into great detail. We'll just give you a flavor of what that is. Okay. So the motion of any dynamical system is basically a differential equation like dx by dt, which is some function on the right hand side. Okay. So now if you, let's say, drop a piece of chalk from some height, just drop it so that you don't throw it, then what happens is it starts falling. So it starts falling because of a force which is acting on it. That force is what you see as f of x here, and that is the gravitational force mg. Okay, and the right hand side is the how the particle accelerates. So that's the dx by dt or d square x by dt square. So essentially dynamic system means it's a time varying differential equation. It's an ordinary differential equation generally. Okay, so and the x in this case could be position. If you drop a chalk or in a piece of any object, it starts falling. If it's falling straight, it is just only in one direction. But if it's falling in 3 dimensions, you are looking at position vectors x, y, and z, and also the unknown could be velocities u, v, and w. The function on the right could be linear or non-linear. For example, if the Galileo's experiment of dropping a cannonball and a feather assumed that atmospheric drag is negligible, so all he got was mass into acceleration m into d square by dt square is equal to mg. M cancels out, so he inferred that when an object falls from certain height, mass of the object doesn't matter, so the cannonball and the feather should reach the ground at the same time if they are dropped from the Leaning Tower of Pisa. This was a thought experiment. I don't think he actually dropped anything, because if he had dropped, he would have realized because of the air drag, the feather takes longer to fall. Okay, so that's when I said it is a linear function, mg. Now, because there is a drag, all you have is that the equation is now different. M into d square x by dt square in the right hand side is equal to mg, but there is an opposing force minus cd half rho v square s. So this term makes it non-linear. That's just an example. And of course, the equation could be a higher order because now it's no longer dx by dt, it's d square x by dt square. However, the dynamic system differential equation is a time-dependent equation. If the whole set is linear, you are free to use Laplace transforms and get a reasonably good quick solution because you get an equation, a polynomial equation in S. I'll show you several examples of that. And in MATLAB, you say root of that equation, give the polynomial with the 6th order, 7th order, whatever, the roots will come out. Look at the roots. If the roots are imaginary, sorry, the roots are complex, and the roots are all real, and the real part is negative, and all that we will discuss. Okay, one quick interesting point here. When the roots are complex, there is an imaginary term. Okay, that imaginary term indicates that there are oscillations present in that. How and why? We'll see if I can cover that a little bit later. Okay, so and sometimes there will be higher order dynamics. It's not only one x. I'm using x dot here. X dot is equal to ax plus b, and y dot is equal to cx plus dy. A, B, C, and D could be constants, could be some other things. So what you have is the variation of x influences the variation of y, and the variation of y increases the variation of x. So it could be an equation. These are just generic cases, just to highlight what I'm trying to address. Or they could be higher order, x like x double dot is equal to ax dot plus bx. Okay, this is, for example, mass into acceleration is equal to some constant times velocity plus constant times the d's. So if you remember your school equations and dropping an object, what is the velocity of an object at any point of time? V is equal to u plus at. U is the initial velocity at which it started falling. So if you just drop it, then u is 0, and the acceleration due to gravity is g. So velocity of an object is initial velocity plus acceleration times the time, right? And the distance traveled would be equal to ut plus half at square, and that comes from basically integrating this kind of equations. So it's common for us to use Newton's laws like F is equal to ma, or in other words, x double dot is equal to F by m. One caution here. These Newton's laws are applicable only in an inertial frame of reference. Please remember that they are applicable only in an inertial frame of reference. So if I'm going to talk about an aircraft flight which is moving in space, the frame of reference unfortunately is not inertial. So you have to fix the frame at the center of the earth or the surface of the earth, and then you have to transform the equations to apply for the moving object. So that increases the complexity. The equations are same, but the difference is that now you have coordinate transformations. But anyway, that's a matter of detail. But just remember, Newton's laws of motion are applicable for inertial frame of reference. So let's say when we have higher order dynamics, x double dot is equal to x dot plus bx, we need to convert them into a set of first order equations. Basically, for example, we have lots of tools in MATLAB and other tools which can integrate a set of first order differential equations. So what you do is you need to convert this into two first order equations. So there's a very simple thing. I'm just revising these. I'm assuming these were all covered in your maths 1, 2, 3, and 4. Just for completeness, I'm just mentioning it here. So if you have a second order equation like x double dot is equal to x dot plus bx, you can convert that into x dot is equal to y and y dot is equal to ay plus bx. What you see here is you have two coupled first order differential equations. From one single second order differential equation, you have reduced it to two first order equations. Okay, and here is a simple thing which I picked up from Erwin Kreyszig's book. How many of you have heard of this book, Kreyszig's book on engineering mathematics? So if you're not, please get a copy of that. I have a copy of that. I'll share it with you sometime. This is the best book for engineering students, and trust me, I read this when I was in your age and in your stage in life. So it's been there from a long time. Okay, and this book is just covers everything an engineering student needs to learn in mathematics. So in that, he has given a simple formula. If you have a nth order ordinary differential equation like this, and you can set, sorry, somebody talking? Okay, so you can break this up into this kind of set of ordinary differential equations. So I've given the reference. It's in the 10th edition, printed page 135, how to convert any nth order ordinary differential equation into n first order ordinary differential equations. So the state space is another way I talked about in the beginning stage. See, the previous one assumes that the equations are linear. And once you have a linear equation, you can straight away use the whatever nth order, fifth order, sixth order, and use a Laplace transform and get a polynomial, convert that into polynomial. But there's another technique which you can use. You can actually use what's called a state space technique, or basically it's a matrix method. Okay, now if you have x dot, it's a vector of x1, x2, x3. So essentially you are saying that dx1 by dt depends on x1 and x3 in the first thing. dx2 by dt depends on this. So you can write this entire equation, this set of first order differential equation I'm showing here, x1 dot is equal to x2 dot and x3 dot and all that, as a matrix equation. So okay, what you have got is x dot is a column vector, A is a square matrix, and x bar is the vectors x1, x2, and x3. So what's the advantage of writing it this way is that you can use matrix algebra, meaning that you can get eigenvalues and eigenvectors, and this is possible even if the system is nonlinear, because we are not going into transformations. Okay, so writing this equation has, as says here, has many advantages. And advantages. Consider the system like this: the simple 2 by 2 matrix you get. X dot is equal to ax plus by, y dot is equal to cx plus dy. You can write that as this. X dot in this case is a column vector x and y. A is a matrix A, B, C, and D, and x and y. Okay, so what are the things you can get from this? Now, if this is a matrix, you can of course compute its determinant, you can compute its inverse, and you can do a whole lot of things. Okay, because there are lots of tools available already for matrix operations. So if you use a Laplace transform technique, and for example, if you have a third order equation, x triple dot, ax double dot, bx dot, cx dot, that automatically becomes x cubed minus a squared minus bs and all that. Now in this case, you are trying to see what are the roots of this equation, s cubed minus a squared minus bs minus c equal to 0. So this is a characteristic equation. So roots of this equation will tell you whether the system described by this nth order, third order differential equation is stable or not. Okay, so this is one characteristic equation. So the roots of the characteristic equation are important. The roots could be complex. It's not that they'll always be complex. They could be complex. So they could have a form s naught is equal to a plus, it should be bi, but okay, fine. You understand that bi is the complex part, a is the real part. Okay. Now the roots of the equations are like this. You have very simple rules. When is it stable? Stable roots all have negative real part. If a is negative in the roots, then the system is stable. Okay. Now what happens if the roots are, let's say all the roots are real, all are negative, then the system is perfectly stable. Okay. And if all the roots are real, but all of them or some of them are negative, there are some modes in which the system is unstable. So now let's look at what happens if these roots are complex. There is a complex part. So complex part automatically means trigonometric solution. There are trigonometric modes, which means there are oscillations. Okay. So if you remember, e to the power I theta will lead into sine and cos parts of it, whereas e to the power of just theta will be an exponential solution. So this, if you really look at it as a solution, e to the power s naught, this will be the exponential part of it, and this will be the oscillatory part of it. So let's assume roots, all real parts are negative, but at least one pair of positive real parts are there. Then it is unstable. Okay. Oscillation, all roots are real, no oscillation. At least one pair of root is imaginary as an imaginary part. It cannot be one root, it is a pair of roots. as imaginary part, then the system is oscillatory. So the reason why people were using this Laplace transform technique is the ease with which you can get this. Okay, but the limitations, as I said, this equation has to be linear. Okay, and that is when you are able to get this simple equation and immediately find out whether the roots are positive or not. Now, just a quick tip here. What happens in this s cube minus a squared minus bs minus c equal to 0? The component c is 0. What happens when this constant is not there? Any quick reply? In an equation, third order equation, if there is no constant, it only means that s is equal to 0 is one of the roots. Correct? Do you get that? So if I give you this equation and if the constant is missing, you will immediately know s is equal to 0 is one of the roots. So that is how theory of equations we can guess in the initial stages. Okay, so let's look at the quadratic formula. Just a revision, as I said, s squared. Now I'm using s instead. A squared plus bs plus c has roots. This parts of it. Okay, so s has two roots, minus b plus minus and 2a. So example, s squared plus s plus 1 is equal to 0 has roots, minus 1 plus minus root of 3 imaginary. So here, because in the real part minus 1 negative, so it's stable, but the imaginary parts are not 0, it is oscillatory. So it's a very simple way of deciding whether the system is oscillatory or not. Now let's go back to the state space technique. Okay, so in this case, as I said, you have lots of linear algebra codes or techniques available by which you can use all the things. So now if I write x dot is ax of t matrix equation, then I can use this si minus ax. So this is basically I'm trying to find the eigenvalues. So in this case, I is the capital I is the identity matrix. Si minus a, determinant of that is 0. The characteristic equation is actually this. So find the determinant. So what is the determinant in a simple A, B, C, D matrix? AD, this A into D minus B into C. Okay. So if you have a 3 equations, A, B, C, D, E, F, and G, H, I, so you'll have an equation like this. So what does it tell us? What happens if the determinant is 0 in a matrix equation? Remember your linear algebra. The determinant is 0. What does it mean? Anyway. Okay. I thought I'll include that in the term test, but anyway, now that you've given out the answer, I won't. So now let's look at a very simple example. This, of course, everybody has included, including Dr. Vijay and Gopal Krishna and all that, but I need it in this context. Okay, the reason I am using the same example, spring, mass, and the damper, is I am going to try and connect what is the spring in an aircraft, what's the damper in an aircraft. Okay, so that correlation we need to understand. Essentially, it's the same thing. I don't want to go into this again. Simple system, you will get has two roots, minus 5 and minus 10. System is stable, non-oscillatory. So same example, you can put it as a matrix equation. Okay, that also has a characteristic equation. It comes out like that. Okay, the only advantage in a matrix formulation is that when the system is non-linear, you're not getting this equation through Laplace transform, you're getting it through eigenvalues. So that is the advantage. So in state space, there are easier ways to find the roots of an equation. They are the eigenvalues. Any n cross n matrix A has n eigenvalues, and you can call them lambda I. Associated with each eigenvalue lambda I, there is an eigenvector. Okay, so this is part of its concept. Now let's start looking at a scenario. Assuming that let's say you're driving around in a motorbike and you ride across a hump. What happens first is that these the springs in your motorbike compress so that you're still in contact with the road, and after the hump they expand. Imagine your motorbike, there is no shock absorber. So what will happen? You'll be bouncing up and down. But that's the reason they introduce a shock absorber, which ensures that while the spring compresses, when it releases the thing, it extends much slower, so that there is a kind of a damping which is involved. Okay, now the same thing happens in an aircraft. Only thing in this case, neither the spring nor the damper shock absorber is visible. Okay, so let's look at different scenarios. I think I'm coming to the closure of this thing, but anyway, I'll try and connect the spring and the whatever the damping forces in an aircraft. So the characteristic equation, continuing that, we can easily get the in the MATLAB. Earlier in my time, we used to use calculators to find this. Now you don't have to bother. So you just have a call Ix function in MATLAB, give it a matrix, and then it will give you the eigenvectors and eigenvalues, all of them together. So a quick example: if x dot is 3, 2, 1, 3, minus 4, 5, you will get the the eigenvalues is minus 1.4, 2.3. Now so that will tell you whether the system is stable, because all eigenvalues are negative real part. System will oscillate about the direction is given here. These are the modes. So the drawbacks of transfer function approach, characteristic equation applied. Both of them techniques get you the characteristic equation, but the characteristic equation obtained through use of Laplace transform is called the transfer function method, and of course they are based on, as I said earlier, principle of superposition, which is not applicable if the system is nonlinear. No information regarding the initial state of the system. That's another disadvantage. System is treated as a black box. So if you talk about, talk to the control system people, they always talk about the plant. Okay, so the question, what is the plant? So the plant has inputs, it has outputs. From the outputs, you take a feedback, give it to the input, and then control the plant. So for them, it's a plant. Now the plant could be an aircraft, or a plant could be a chemical factory producing vaccines, or the plant could be a car, or the plant could be anything. Okay, so for them it is a black box. Okay, and you are just an observer. You are saying that, okay, if I give this input, this is what comes out, and this is not what I expected, so I want to change the input. Basically, it doesn't take into account what is inside the box. For them, it is just input output. Okay, now there are multiple inputs and multiple outputs. It becomes extremely difficult to use this transform technique, and it's also difficult to perform transfer function analysis on computers. So how do you do a Laplace transform, inverse transforms? There is a in a book there is a list of Laplace transforms and their inverses. You just pick out one of them and then that's a solution. It's kind of difficult to do this in the computer. It's not that impossible. It's more difficult. So quickly, advantages. After this, I will stop. State space, of course, is what's called a modern control method. Takes the differential equation that describe the time domain of the system and analyzes them in vector form using state variables. So essentially, whether the differential equations are linear or non-linear, it doesn't matter. So you can still, and it's also easy to evaluate the system via simple matrix algebra, whatever is already a lot of computer tools, subroutines, and procedures are available. You just have to call them whichever one you want. Of course, you can have multiple inputs and multiple outputs. System output is evaluated, doesn't matter. The classical control systems such as PID, proportional, integration, differential, rely on complex Laplace transforms and Fourier transforms. They convert it into domain representation given as complex set of differential equations. So basically that's it. Even the state space approach, you are actually looking at the entire system internally. So when you're deriving those equations, you are interested in what is the lift produced, what's the moment, which is producing what, how much is the rate of change, and all that. So essentially, this method gives you a full view of what the system inside is. It's no longer a black box. The internal state of variable. These state variables describe the system and its response to given input. The major benefit of the system is one, linear, non-linear superposition is not valid, so you can have non-linear also. It could be time varying and time invariant. Whereas in the transfer function method, you have a plan, you give it an input, you look out what comes out, and then change it. Okay. A simple example or the straightaway example is when you're trying to have a shower, you turn the hot water. What happens? You wait for a second and then see how hot the water is. It's too hot, you turn the cold tap. If it's the correct temperature, you have a bath, or if it's too cold, you turn on. So basically, You're not interested in what's happening in the geyser. You're only interested in what position of the tap you did and what's the outcome. Okay, so whereas in a state space approach, you can have a complete view of it. And if you're once you see there are unstable modes, unstable roots, then you can actually integrate the differential equations in time using ODE solvers, and then actually track each variable and figure out where and when it goes into uncontrollable state. Okay, so there are many advantages to that, and most flight dynamics people use this technique. Initially, of course, you could use the transform technique conceptual design stage, but when you have more and more data, equations become nonlinear, and then you're forced to use this. So this is what I'm going to stop here. The topics to be covered in the next will be dynamic behavior. How do we apply what all we talked about so far, and how we can apply these thoughts or techniques into handling what an aircraft does, okay, or how an aircraft is going to behave. So essentially, we'll also have examples of Laplace transforms and state space method, and then some simple and interesting results obtained using spring mass damper model. Okay, so that's what we are going to be covering as we go ahead. And I'll stop here. I don't know if you have another class after this. In case you have, it's fine. We'll be stopping a little early. So this entire thing, what I shared with you, I had already recorded, and I'm sure whatever I have spoken there will be different from what I did here, because it's not from a script, it's extempore. So there may be some conflicts, doesn't matter, you listen to both. That is, if you have the patience, and then try and understand. If you have any queries, please send it to the group email ID, WhatsApp, so that when I reply, everybody else has the same answer. Is that fair? So if you send me a personal query, it's not that I mind, but if somebody else has the same doubt, then it won't help them. And the idea is to help everybody, so that all of you understand whatever the subject is being taught. I understand that it's not the same as me standing there face to face and doing it, but these are difficult times, so we have to make do with this online classes. So okay, I am stopping here, and after the class, the recording, whatever recording comes out, I'll share with you again once its recording stops. Okay, so any questions now? We can take another 5 minutes, and then we'll close the class. Are the class reps there?
Yes, sir.
Yes, sir.
Remember what Dr. Raja said, you need to take a snapshot of all the people who have attended, and keep that as a record, because apparently this is needed for the audits.
So there's an option now. You can use saying load participants.
So where is it, Ma?
So download.
Oh, it's the magician talking, right? Merlin the magician. Okay, where is it?
Sir, it's under view participants.
Okay. View participants.
There is option download.
Okay. Yeah, all of you show up here, but how do I take a picture of this or whatever? I can store them, the list.
Yes, sir, you can download that.
Thank you. Remember, it's not for me. It's for the record. Okay. So everything is fine so far? All right, I'll stop here. One more question, Merlin. When you say download, where does it store the damn thing?
In your downloads, system downloads.
Okay. Thanks, Ma.
Yes.
Okay, guys, take care. Hello. In last class, we talked about the initial introduction to the dynamic stability. So we'll go ahead and see how that dynamic stability characteristics can be applied and get some useful results for longitudinal stability of the aircraft first. Then we'll go to the other parts of the stability later. So objectives at the end of the session, students will be able to first explain the necessity of evaluating dynamic stability, derive similarities between generic spring mass damper system, which you have studied properly in structural dynamics and vibrations other places. And similar concepts can be applied to aircraft degree of freedom. Derive some useful results by using a simplified model for longitudinal dynamic stability. Eventually, we'll have to derive the 6 degrees of motion equations, which are differential equations, extremely nonlinear differential equations, which need a lot of geometric and other input data from the aircraft, which is not usually attempted until the aircraft design stage has reached some sort of maturity, because the kind of numbers and parameters you need will not be available until the aircraft more or less has been frozen, because it needs moments of finish, mass moments of finish, and stuff like that. So initial stages we can do with simplified analysis. So we have studied about static stability in the previous classes. So we now look at why we should study dynamic stability. Static stability just indicates that if there is a disturbance, the aircraft has a tendency to return to its equilibrium position. So now we are now interested in seeing in the time history of its return to the equilibrium position. How much time does it take to come to the equilibrium position? Is it going to oscillate? It's not going to oscillate. If it's going to oscillate, how many? What is the frequency of oscillations, the wavelength, and all that kind of thing? Now let's do a quick recap. Assume that you have a system which has positive static stability and also positive dynamic stability. So in this case, there are two possibilities. If the damping, whatever damping is not very high but adequate, then the system, once it's disturbed from this stage to this, it goes into an oscillatory mode like this. Why it goes into an oscillatory mode, we will talk about in the next couple of slides. If the the damping is very high, then of course the aircraft disturbed goes to this position, and then of course it comes back slowly, steadily into the equilibrium position with no oscillation. So in this case, this is called a highly damped system and a lightly damped system. So just remember figure A and figure B. Figure A refers to positive static stability and positive dynamic stability, but the damping is light. In this case, it's very heavily damped. One simple example of a very heavily damped system is some of these doors in offices you see with the dampers at top of the harder you push, the more resistance it will do. You open the door and leave it, it will close down slowly, it won't oscillate, and that's an example of a highly damped system. So just an overview of the static stability. The system, because it has static stability, which as we have discussed earlier, is an initial tendency when displaced from from equilibrium to move back towards equilibrium. So as this system reaches equilibrium, the forces and the moments which move it to there also generate a kind of momentum which causes it to overshoot and go beyond the equilibrium position. And this is something which is you can simply observe even in an athletics race, let's say in a 100-meter dash. The runners don't stop exactly at the end of the race. They continue because of the momentum they have built need to be reduced slowly for them to be able to stop. In this case too, when the aircraft is disturbed, if the static stability is positive static stability, then there is a forces and moments which start moving it towards equilibrium. But while doing it, it kind of generates a certain momentum which makes it overshoot the equilibrium position, meaning that it goes out of equilibrium again, and the same the forces which started to move it in the equilibrium will come towards it again, and again it will overshoot the equilibrium. So this kind of oscillatory behavior is what you saw in this slide. So it moves towards equilibrium, overshoots, moves back towards equilibrium, overshoot again, and then a couple of oscillations, a few more oscillations, it comes back to stability. So this process of moving forward and overshooting and then moving towards equilibrium again is, as you know, is called oscillation. And we are interested in the time history of the oscillation. Okay, so what is the frequency of the oscillation? How much time does it take to come back to its equilibrium, as in the figure in the previous slide? So that over the period of time, the system gets closer to equilibrium, then the system is said to have positive dynamic stability. Figure B there showed a system which was highly damped. So when the aircraft is disturbed, it comes back towards equilibrium, but it doesn't overshoot because the damping is high. It just asymptotically reaches its equilibrium position. Now let's look at the other case where the system is positively has positive static stability, but the dynamic stability is neutral. In such a case, what happens if there is no damping? Of course, there is no such thing as no damping in nature. Damping is always there. So what we are looking at is very, very low damping, in which case the system goes into a continuous oscillation. It moves towards equilibrium, overshoots, moves back, and overshoots and comes back. So this continues for a long time, and we can almost assume that it's a kind of constant amplitude oscillation. So that's the case where static stability is positive and dynamic stability is neutral. If both of them are neutral, stable, static and dynamic, so what happens is the aircraft is suddenly pushed into a new speed or a new altitude or a new heading. It stays in that, it doesn't recover, it doesn't come back to its equilibrium position. So that is what happens when both of them are neutral. Now the other case left for us to discuss is what happens if the static stability is negative. So let's look what happens if it's negative. If static stability is negative and the dynamic stability also is negative, this is a situation where the system diverges immediately. So there is a disturbance. It not only doesn't come back to equilibrium or stay in whatever disturbs it, it goes beyond control. So this is what happens. So a disturbance just goes away like that. But suppose the static stability is positive, but the dynamic stability is negative. Then because the positive stability is positive, the static stability is positive, it moves towards equilibrium, overshoots, it moves towards equilibrium, but this time the overshoot is larger. Eventually the overshoots become larger and the system goes into a divergent mode. Here the amplitude is increasing. Okay, and this is the case where you have a positive static stability, but the dynamic stability is negative. So the oscillations will continue with increasing amplitude. So in the static stability study, we were interested in how it's going to respond to a perturbation. But it's not only that, it's not enough if it returns back to its equilibrium. The pilot and the passengers would be happy only if the flying or the handling qualities of an airplane are quite good. So this is defined by how the dynamic stability behavior happens. In essence, we need to understand how the aircraft responds over time. Okay, response over time obviously means a differential equation in time, and how the solution to the differential equation behaves. In this case of an aircraft which has 6 degrees of freedom, you have 6 differential equations, each one of them, 3 translations and 3 rotations, and also the forces generated are different. So we will eventually derive the 6 degrees of motion equations. We'll probably not go into solving them because it's very complex and it's out of scope of this subject here at this present. So as before, we can use simple spring mass damper example, what you have studied in the vibrations class or the structural dynamic class. In this case, of course, these springs and masses, the dampers are not visible. Okay? And it also means that in this case, the spring could be a regular spring and also a torsion spring. Well, what I mean by that, I'll come to in a couple of slides from now. So let's see how we apply all these ideas to understand the dynamic stability, longitudinal dynamic stability of an aircraft. We're talking longitudinal dynamic stability because this is the simplest scenario. You can only do this we can do this without actually looking at yaw and roll. If you go into lateral dynamic stability, either yaw or roll, both because they are coupled, the system becomes much more complex. So for analysis, for understanding, we'll start with the longitudinal dynamic stability. So why do we need to do this? In order to be able to fly the aircraft safely, we need stability. Steadily, we need equilibrium, and one place to another, we need controllability. It's not enough if the system is just stable. We also need to be able to control it. in essence, we need to be able to study the behavior of aircraft forces, which is existing forces like gravity and the applied forces like thrust, but there are also derived forces like lift and drag and side forces, which are a result of applying thrust and going forward. And it also comes along with moments, rolling, yawing, and pitching. So all this could be, of course, could also be induced by control surfaces. For example, if the pilot wants to pitch the nose up, he just deflects the elevators, or if he wants to roll, he can deflect the aileron. So it could be controlled by the, it could also be induced by changing the control surfaces. A quick recap of the control surfaces. What you see here are three primary control surfaces: ailerons, elevators, and rudder. So lateral control, meaning rolling, is controlled by ailerons in this way. Pitching moment is controlled by the elevator up and down. Yawing moment is controlled by rudder deflected this way. While rolling and yawing are coupled motion, which means that you have to consider them both together. Longitudinal motion is uncoupled, so you can study this without looking at rolling and yawing. And that is only elevator up and down movement or any disturbance caused by gust. A quick recap of the static stability. What you see here is a simple traditional conventional aircraft with the mass or the weight acting at the center of gravity here. The lift acting from a center of pressure here upwards. Lift, W means wing lift. There is a similar lift from the tail part of it acting at this point at a distance L from where the lift is acting. So if we take moment about the center of gravity, you have two terms. One is the moment inherent in the aerofoil itself, that's called m0. Also moment generated by the lift force because of its distance from the center of gravity. So if we consider h0 as the place where lift from the wing is acting, and hc is where the weight force is acting, the difference between this is h0 minus h into c times lift generated by the wing. Now this has to be offset by the lift generated by the tail. Don't worry about the direction of the tail lift, it is vectorial. So depending on whether you need to make nose down or nose up, you can take according directions. Now this acts at a distance L plus also h0 minus hc. So if you look at this equation here, so if you take moments about center of gravity, m0 minus h0 minus h into c bar times lift from the wing and lift from the tail, and also separately you have to subtract the lift from the tail multiplied by L, this part. And of course, if the thrust line is above the center of gravity, which can sometimes happen because of locating the engine and other things, so you need to, if you can take that into account, this term, the drag too doesn't have to act along the longitudinal axis. It could act above or below the axis, let's say at the distance ZD, then you can take that into account. E into ZD and D into ZT will give you the moment. So this kind of boils down to the simple equation. Just to recap, I don't go into more details than that. So overall, if you see, your airplanes are generally designed to be in equilibrium during level flight, meaning approximately constant altitude, heading, and airspeed. However, such an equilibrium is not possible every time a disturbance is encountered and the airplane begins oscillating in pitch, altitude, and airspeed, and continues to do for a long time. It would be very, very uncomfortable if it's a passenger planes, and uncontrollable overall. The statically stable aircraft, as we discussed earlier, will tend to oscillate about the equilibrium point. So it's in our interest to ensure that it doesn't go into uncontrolled oscillations, or it is damped out very fast. So that's why we are looking at some kind of analogy between a spring mass damper system. Look, just imagine you are going in a car and you hit a road bump, which is pretty common in Indian roads. What happens if the car or motorbike goes over a road hump is the car suspension ensures that the car goes up and down. So there is a suspension in a car which is ensuring that the passengers inside are comfortable and the oscillations are quickly damped out. And so how does this affect the airplane? What happens in an airplane ride? Of course, you don't see the suspension, but it's invisible and it's there. So if we look at trying to compare with a car, there should also be a shock absorber present. Otherwise, no, it will go into an uncontrolled oscillatory mode. You just remove the shock absorber in your motorbike or car and see what happens. So where is the spring or where is the shock absorber in an aircraft which is flying in air? Okay, so this is something which we need to understand. If damping is present, it has to be present in all degrees of freedom. Only then the aircraft would be said to be dynamically stable and well-designed, controllable aircraft with good handling qualities. So the term damping refers to any force or a moment which opposes the rate of change of a particular degree of freedom. Meaning that if the aircraft tries to accelerate, something should slow it down. If the aircraft tries to nose up, something has to push the nose down back and things like that. So the simplest form of damping is when the opposing force or the moment it generates is directly proportional to the rate of change in a given degree of freedom. So going back to the example I talked about, the doors with dampers fixed there. If you move the door slowly, the resistance is smaller. If you try to open it faster, you will find a faster resistance. So that's basically the damping is dependent on the rate of change of the degree of freedom. So the faster you push, the more damping will be there. So let's look at a simple example where the damping force is a drag. Drag, as you know, is a loss creating something which saps the energy of the system. So we can consider this as a damping effect. Let's look at an aircraft which is flying at the forward velocity which is disturbed due to a gust. Let's assume that the aircraft is flying at a speed or a velocity higher than the minimum drag. And we'll talk about that, why that is important. Let's say it's flying at this velocity where it is on the right side on the higher side of the minimum drag. So what happens if there is a sudden gust and the aircraft velocity increases? Let's say there is a tailwind which hits it and the aircraft velocity increases suddenly. So what happens is if the velocity increases in this direction, the drag increases, right? And since the drag is a dissipating force, what it does, it slows down, reduces the velocity and brings it back to whatever was the original velocity. A key point I want you to note here. Remember I said that when you're flying at a velocity larger than the velocity needed for minimum drag. That is very, very essential. So the whole argument that the drag reduces, increases and the velocity reduces, eventually bringing back stability, is applicable only in this part of the velocity. Okay, so the above argument holds only if the aircraft is flying above the minimum drag velocity. If it's flying below the minimum drag velocity, then the system is unstable. Now I leave it to you to figure out why. Just look at the same arguments I talked about in the beginning and try and apply that arguments. What happens with the velocities here? Okay, then see why it is unstable. But drag is a very small force compared, let's say, to lift, which is about 10 times or more in a well-designed aircraft. So therefore, any damping produced by drag is also much smaller than possible if lift were the opposing force or the damping force. A small damping produced by the drag force to any change in the forward speed produces a dynamically damped motion, often called phugoid motion. This is a lightly damped long period oscillation in the airspeed, altitude and pitch angle, sending the aircraft into a nearly constant amplitude roller coaster ride through the air, where eventually it will come back to stable position. Let's say, in this case, to continue with the drag, the angle of attack in this case doesn't change much. Okay, only the velocity increases, and because the velocity increases, CL or CL is not changing, meaning the angle of attack doesn't change. Because the aerodynamic forces motion is only drag, and it's applied tangentially to the flight path. So the phugoid mode can be excited also by the pilot by varying the throttle without changing the angle of attack. Let's say he holds the stick in the same position, but suddenly increases the thrust rating of the engine. Then the velocity increases, or it could be because of a head tailwind which was unexpected. The aircraft goes into some kind of accelerated mode and then comes back to it. Now let's look at a damping example where lift is the damping force. So unlike in the previous case, just a moment. So let's look at this aircraft model. Okay, and instead of the velocity being increased, let's say there is a gust which pushes the angle of attack only. So it just goes up. So what happens if the angle of attack increases is that the CL increases because CL depends on the angle of attack. and the lift force generated. Lift force being much stronger than the drag. So the pitching moment and the lift force which govern this type of oscillation, which are larger than that of drag. So consequently, the oscillation in angle of attack is much better damped, and for most aircraft, it will persist maybe to 1 or 2 seconds and is damped out very, very quickly. Okay, so this mode of longitudinal oscillation is called short period mode and is normally excited by sudden elevator input. So let's assume that the pilot suddenly moves the stick forward or backward and back into the equilibrium position. So that small disturbance in elevator will cause the angle of attack to go up and down, and then of course it's damped out very, very quickly because lift and moment produced by the lift are much stronger than the drag force. So what really happens in this case is, as the airplane is pitched nose up during the oscillation, the increased angle of attack on the wing leads to increased lift. In a statically stable aircraft, this increases the nose down moment. Remember, the lift force is acting behind the center of gravity. So if the lift force increases compared to that of the weight, then there is a nose down moment. So what happens is, if the angle of attack increases, there is a nose down moment generated and the aircraft tends to come down. Okay, so this when doing this, the tail which also moves up and down because of the aircraft pitching right. Remember, the aircraft always pitches at the center of gravity. So when this happens, you can see the tail is moving at a faster rate, which depends on its distance from the center of gravity, right? So if the distance is large, then it will move faster. So this motion, the pitch motion, alters the angle of attack which the tail sees. As the tail produces a force, lift force up or downwards, depending on the angle of attack it sees, this changing angle of attack also has an effect on the pitch rate of the aircraft. So the changed tail lift immediately translates into a nose down pitching moment, thereby damping the oscillation. So similar damping is produced by a canard, if it's an aircraft with a canard, but with the lift in the opposite direction to that of the tail. But the damping motion produced by both of them are similar. So now what happens if the aircraft is tailless, just like a delta wing aircraft or like Mirage 2000 or a Tejas? So what happens if there is neither a tail nor a canard? In this case, the short period damping would be rather small, and it will take a longer time to do that. So this needs to be corrected externally. Okay, if there is no inbuilt damping because of that, some additional thing has to be done. So what is done without going into great detail is that ailerons which are there in a tailless delta aircraft like Tejas are deflected 180 degrees out of phase with the pitching oscillation, meaning that these oscillations are aileron is deflected out of phase. So what this does is, it damps out the oscillation. And how do we ensure that the ailerons are deflected out of phase and at what rate? Generally, a rate gyro is fixed into the aircraft, and that generates the necessary signals which then drive the amplifier and drive the motor in the opposite direction. Such a system is commonly used in tailless aircraft and is termed as a pitch stability augmentation system. Without that, the aircraft handling would be rather difficult, and this of course system is there in Tejas. Detailed discussion of this kind of systems is beyond our present scope. Maybe when we cover later in the master's course, we'll talk more about it. Okay, now when we say dynamics, obviously, as I mentioned earlier, we are talking about differential equation with respect to time. Okay, so when a system is in equilibrium, only summation of all forces and summation of all moments with respect to center of gravity at that instant where it is equilibrium is equal to 0. Only when the sum of the forces and moments are zeroed out, that system is supposed to be in equilibrium. Just to repeat, static stability means for a given disturbance, the system will return to its equilibrium to trim state. And no indication or measure of how that path follows, and for that we need to study the dynamics. So we will try and extend the spring mass damper analogy and try to see how we can understand this. Okay, now when we say differential equations, we need to be able to derive them for an aircraft. As a first step, let's take a very, very simple case and make a drastic assumptions which are not really true, but which will help us to get the sense of what we are looking at. So let's assume that the aircraft is rigid. So what is rigid? What's the meaning of a rigid aircraft? Rigid aircraft means that the lift produced by the wing does not deflect the wing, does not distort it. That means the whole aircraft is infinitely rigid and it doesn't change in any kind of shape. We also assume that the mass is constant. This, of course, is strictly not right because the fuel is being consumed. But in initial analysis, we can get away with this kind of thing. So why we need to assume constant mass is because we want to bring an analogy of spring mass and damper system. There the spring constant and the mass are not changing, neither is the damping coefficient. So under these above assumptions, all our equations of motion will be linear and they will have a form like this. So what you see here is x dot is equal to some factor a, which could be constant or variable, times the function of x, which changes with time. It could be a function of time. It could be sine omega t, cos omega t, exponential, whatever function. Okay. So in this case, of course, we function could be ax. Why we are doing? Why are we going to all this trouble to linearize and simplify? Is it's easier to understand, easier to visualize, and also give you a reasonably good insight into how the system behaves without going into the full-fledged 6 degrees of freedom simulation. So stability of linear systems is very simple. So if x dot is equal to a is equal to x, is stable if a is less than 0, and unstable if a is equal to or greater than 0. This is a very simple system, so you can easily check it out. If dx by dt is equal to ax and a is positive, that means x is continuously changing. It's a divergent system. So if a is positive or 0, then the system is unstable. Okay, so let's start with a very simple single degree of freedom. Okay, assume that the aircraft is fixed at the center of gravity. So what we mean by this is it is fixed at this point. It cannot go up or down. It cannot do this or this, or it cannot do this. But it can only do this, pitch up and down. It's just assume that there is a hinge here and the aircraft can only pitch up and down. It's fixed at the center of gravity. This is the kind of thing happens in the wind tunnel. So we're going to study what happens if the aircraft is fixed in a tunnel, let's say, and only degree of freedom allowed is its nose up and down and none other things. Now, Newton's second law for a straight line motion or a non-oscillating or rotary motion is force is equal to mass into acceleration. A similar law for a rotating system is moment is equal to moment of inertia times angular velocity, or m is equal to I theta double dot. In our example aircraft case, let's assume that theta is the angle of attack because that's the only angle it can vary. Of course, in a real aircraft, there you have to consider all angles like pitch angle, yaw angle, and roll angle, and all that. But in this case, since the only angle, only degree of freedom I am allowing is pitch, that is alpha double dot. So B is the moment of inertia about the pitch axis, and mcg is a moment with respect to center of gravity. If you add them up, it should become 0. This is a very simple x double dot mx is equal to constant, kind of spring mass damper equation kind of thing. So this, to pictorially show you, if you fix the, let's say, I'm representing the airfoil here, it could be the complete aircraft. It's fixed at this point in the center of gravity, and there is a torsion spring. So I'm sure you all must have seen torsion spring example in vibration classes. So this spring only resists the direction in the rotary motion. And when there is a sudden increase in the pitch, let's say the theta increases, that's what happens. Let's look at this. So lift depends on dynamic pressure, which is half rho v square s, represented here as q, times the wing area, times the, in this case, what you see here, dCl by d alpha. Because alpha is changing, I cannot have a constant CL. I need to find what is the new CL for a new changed angle, which is theta naught plus theta. Theta naught is the original angle. Alpha naught is original angle. Theta is the disturbing angle. So when you take the CL into CL suffix alpha, what it means is it's a dCl by d alpha. All of you have seen the plots of CL versus alpha. Slope of that curve is this. So when you want to compute a new lift coefficient from a given alpha, you look at the increase in alpha and multiply by the source. So this is the simple system like this. So typical 1 degree of freedom system. Okay. Now the moment of inertia. What we consider look here in this case is assume that the stick is fixed, meaning that the elevator is frozen, it's not allowed to move. its elevator is float at an angle. In stick fixed condition, the moment with respect to center of gravity related to angle of attack is simply through, it's related through fixed static margin. Stick fixed static margin is what we have derived. So I'm reproducing here, which is the Kn. DCM, DCL is what we are interested in. This is slope. As long as it's negative, then the system is stable. So if we take the moment with respect to center of gravity and changing alpha, so what you have is dynamic pressure half rho v square s into, because it's a moment, you non-damaged life with C bar, multiplied with moment coefficient. And as we discussed earlier, moment coefficient depends on moment with respect to m naught, which is 0, not lift not acting. It's inherent moment for the moment because of the aircraft geometry, and a static margin here, h naught minus h into CL, and a tail volume ratio. So this entire system can be simplified and written as minus times mc, because it's opposing force, rho v squared by c into kn into a in this case is dc CL alpha, that is the dcl d alpha, into times the alpha plus mcg. This is the inherent moment. Let's say we ignore the inherent moment because it's coming from the overall geometry of the aircraft. It doesn't change with angle of attack or with respect to time, so we can ignore it while studying that. So this whole system reduces to very simple equation here. Beta times alpha double dot plus rho v square s into c bar by 2 into the static margin into the dcl by d alpha slope times the alpha. Okay, so the other equation is derived, of course, by ignoring this factor. We can, because it's, as I said, it's inherent geometric factor, doesn't change with time or angle of attack, we can ignore it. Now, the previous system is a first order differential equation, linear differential equation in time, and you can expand this equation and get a solution in terms of alpha is equal to e to the power j omega t. Omega square is the term here, and if the roots of this equation are real and positive, if the roots are real and positive, system is unstable. If the roots are real and negative, the system is stable. If the roots are imaginary, then the system is stable but oscillatory. Okay, so that's what is the system here. So now let's expand our understanding and look what happens when the system has 2 degrees of motion, in which case the aircraft not only is pitching up and down, can also move up and down, in the z direction. That is, it's not only doing this, it's also going up and down. So doing both. So it has 2 degrees of motion. Now there is change in z as well as change in the angle. So in this case, we are allowing the change of angle of attack and height both. That's why it's called 2 degrees of motion. In such a case, the equations become a little more complex and the aircraft behaves as shown in figure. So what really happens in this case, let's say the aircraft is at equilibrium in location A. U is the velocity which is equal to V naught. What is the equilibrium velocity? And lift is equal to mass, weight. So it's in equilibrium. Now suddenly there is a disturbance which pushes the nose down. So when the nose goes down, what happens is the aircraft goes into a dive, which starts going down. Because it's assisted by gravity while going down, the velocity increases. When the U, aircraft velocity, is greater than equilibrium velocity V naught, which means obviously that the lift produced is larger than the weight of the aircraft. Because lift is larger than the aircraft, it starts climbing. And because of the damping not being so much, it overshoots the equilibrium position and goes up. Once it's going up, it's flying against the gravitation force, so the velocity starts reducing. And U now velocity is less than the equilibrium velocity. Lift becomes less than that of weight. At the point C, it goes back into a dive. So this motion, as you can see, is going up and down. Essentially, we can treat it as an interplay between kinetic energy and potential energy. Kinetic energy represented by velocity, potential energy represented by altitude of the aircraft. If the damping is adequate, then the oscillations will die out, else they will grow, taking the aircraft completely out of control. Okay, so we'll stop here. In the next lecture, we will look at, hopefully derive the 6 degrees of freedom equations. And because we are, these, Newton's laws are applicable to inertial frame of reference, but the aircraft is moving, so we need to be able to derive the equations in inertial frame of reference and then transpose it to the aircraft frame of reference, for which we'll also be learning how to transform from one frame of reference to another, and Euler angles of transformation matrices and stuff like that. Okay, I'll stop here, and then if you have any questions, please send me through SMS or email, and then I'll try and answer them.
When people say tailless aircraft, it's only we're talking about the absence of the horizontal tail. For example, many of you are given examples of Mirage 2000 and Tejas and Saab and all that, but all of them have vertical tail. Very few aircraft, maybe one or two, are there without the vertical tail, and that's the stealth bomber. Okay, so basically, what we are looking at is how big should be this vertical stabilizer, and what is the requirement for directional stability. As in this case, you have a small deflectable body that's called a rudder. In some cases, the whole tail could be movable if you want more side forces, more control authority. So what actually happens if you observe this black part which deflects? If it deflects in this direction, that produces a force in the other direction, and then the aircraft yaws in whatever direction the pilot wants to do. So just a little bit of recap on the side force. So if the side force is applied instantaneously and removed, just like when you hit a ball or a tennis ball or a cricket ball, the side force F is applied instantaneously and removed. When that happens, the velocity which was going in this direction, initial velocity, is deflected in a straight line and that goes like that. Okay, this is the instantaneous applied, but in an aircraft which is turning, the side force is applied continuously for a period of time. Always a side force is pointing towards the center. This will ensure the direction of the aircraft takes a nice circular path, and when the final velocity direction is reached, this side force is removed. Okay, so this is what happens when a pilot wants to change direction. It's not like this. It is a smooth directional change which happens. So essentially, static directional stability is a measure of the aircraft's resistance to side slipping. So what we mean by side slipping is the aircraft tends to go towards the sidewards, and this leads to a large drag and a loss in altitude. There are cases where the pilot deliberately initiates the side slipping maneuver in order to reduce the altitude or dump the lift to a greater extent, but that is a very rare maneuver. The greater the static directional stability, the quicker the aircraft will return into a relative wind, which is not aligned to the direction axis. So what happens when the aircraft is flying? Let's say the aircraft, if I can use this model, I hope you can say this, if the aircraft is yawed like this, but going in this direction, there is going to be a tremendous drag. So the aircraft tends to align itself in the direction of the in which the wind is coming. So this will, of course, reduce the drag, and that is the idea of a directional stability. So whenever the aircraft is, let's say, flying for long times in cruise conditions, and the small perturbations which side gusts and all that involve, the aircraft automatically aligns itself towards the direction of the flow. So in an equilibrium condition, an airplane flies so that the yaw angle is 0. That automatically minimizes the drag. Okay, to have static direction stability, the appropriate positive or the negative yawing moment should be generated to compensate for negative or positive side slip angle. There's a little bit of confusion which people have here. I'll try and clarify that here. So consider the figure on the right side. Okay, and if the original aircraft is flying in this direction, the side wind comes in this direction. Okay, the wind is coming at a direction called beta, at an angle beta. So as far as the pilot is concerned, or the aircraft is concerned, the aircraft has yawed in the negative direction, in this direction, minus side. Okay, because the relative velocity combining the side wind and the forward velocity u is in this direction. So by definition, the positive side slip angle equals to the negative yaw angle. So don't get confused with it. It's just a way of defining how it is to be done. So what happens when the wind comes in this direction is the aircraft automatically tries to align itself towards the wind, because that is how the drag is reduced. Now, some of you must have played shuttlecock. You know, whichever way you hit the shuttlecock, it aligns itself such that the drag is minimum, and the cork side part of it always comes down. The feather is always behind it. You never see a shuttlecock coming feather first towards you. That's because the minimum drag is the way in which the shuttlecock moves actually. What actually happens when there is a side wind like this is a vertical fin is after all an airfoil section, just like a wing. So what it sees is at an angle of attack. It's like instead of calling it angle of attack, we call it angle of side slip. So because this angle is coming in this direction, there is going to be a force which is being produced. So this force, I've written it as a lift suffix F, F standing for fin. So once this happens, this force generates in this direction, the aircraft automatically turns as indicated in this end vector n. So the natural moment, if the aircraft vertical fin is designed correctly, is to align itself automatically towards the wind direction. So this yawing movement is stabilizing because it causes to correct, to move towards the wind direction, avoiding side slip. If this doesn't happen, because the wind is coming in this direction, there's going to be more force, which is going to move in the sideward direction. And an aircraft moving in the sideward direction, the drag is so high, it will start losing altitude. Okay, that's not a very desirable thing to do. So if you want to ensure that the static stability with respect to direction is built into it, so that our aircraft automatically aligns itself towards the coming wind. Okay, so this is just picture of that. So what we are trying to do is the condition of aircraft to be direction stable is established as dCn by d beta being greater than 0. Okay, please remember dCn is the side force which is generated with respect to beta. This is a positive slope. Okay, when we talked about the pitch stability, that was a negative slope line. In this case, it's a positive slope line. Another point I would like to stress here, whenever we talked about the pitching moment, dCm by dCl, sometimes I use dCm by dCl and sometimes I've used dCm by d alpha, because essentially CL versus alpha is a linear curve, at least in the linear range. CL, lift coefficient, and the angle of attack are related through the CL alpha curve. However, we cannot replace dCn by d beta by dCn by dCl, because lift coefficient is not dependent on beta. Okay, so while you can replace dCm by dCl by dCm by d alpha, you cannot do that. You still have to do dCn by d beta only. Okay, this is just a figure to show you some typical numbers of what would be the Cn beta values in terms of kg meter. So there are two curves here. We'll talk about the second curve later, that is with the dorsal fin. So if the original aircraft was this empty circles or unfilled circles, it varies like this. As you can see, it's a positive sloped curve. There's another curve here with inverted triangles called dorsal fin. I'll talk about it later, but just remember, this has improved the static stability, the dorsal fin. So we'll cover that a little later. In a direction static stability, sometimes referred to as a weathercock stability. This weathercock is you must have seen in airports. There's a hollow cloth sock. It's called winged sock, like a socks with open ends, which is flying all the time near the airports. That automatically aligns itself to the wind. So this indicates to somebody as to which direction the wind is blowing. Okay, so the main contributor for static direction stability is, of course, the vertical fin, a vertical tail, or sometimes it's called the fin. Here, both the size and arm of the fin determine the directional stability of the aircraft. Essentially, we are looking at a force generation and a moment generation. So what ensures the yaw stability is the moment generated with respect to the center of gravity. Okay, for the moment to happen, there should be a force generation and a moment arm. Okay, so the further the vertical fin is behind the center of gravity, more static directional stability in the aircraft will have. Okay, so that is one of the reasons in the archery, if you see bows and arrows, the arrows have a feather at the back. That's basically gives it a directional stability. All rotational motions, as you can understand, are with respect to center of gravity. So, and this directional stability refers to motions around the normal axis. Okay, now there are main contributor is fin. We'll return back to that, but there are other components of the aircraft which also help in the static stability, especially the directional static stability. So look at this figure on the left. Assume that the aircraft is flying in this direction and the wind has a side component and it's coming in the blue arrows direction. And this is the center of gravity. As you can see, the area behind the center of gravity, including the fin, which is facing the side wind, is much larger than this area ahead of the center of gravity. So the drag, because it's going to be a drag here, of this yellow part is going to be larger. So what does it do? The drag in this case will be in this direction. So what you see, the aircraft will turn as shown in the blue circular arrow and align itself towards the incoming wind. Okay, because this is basically the fuselage effect. So fuselage 2 has a certain amount of stabilizing effect in terms of directional stability. It's not only the fin. Fin is the main contributor, but the fuselage 2 contributes to it, as do other components. So the sweep back, most of the aircrafts now have sweep back, except for the very low subsonic aircraft or very low velocity subsonic aircraft. Most of the aircrafts have sweep. Typically, passenger aircrafts, the sweep is around 30 to 35 degrees. If you want to fly higher Mach numbers, then the sweep can be much larger. So what happens when the aircraft has got a sweep? Of course, this one model doesn't have a sweep, but assume it has a sweep and it turns in this direction. So this part of the wing, the sweep angle is reduced. Let's say the original sweep was 30 degrees, and if the aircraft has yaw 5 degrees, the sweep in this direction is 25. Sweep in this direction is 35 or 5 plus. So what it does basically is two things happen here. One, because the sweep back is reduced, the frontal area, which is creating the profile drag, is larger. So that the profile drag increases. But another thing also happens. Okay, I think I clicked the wrong button. Another thing happens here. This is the figure I was talking to. So because the aircraft has yaw to the left, the sweep angle here, relative sweep angle, geometrically the wing is same, but what the wind is seeing is slightly reduced sweep angle. So what happens when you reduce the sweep angle of a wing is that the lift generated is larger. Okay, now if the lift is larger, what you have is larger induced drag. That's one part. The second part, as I said, now this is showing a larger frontal area compared to this, essentially because of the direction of the wing, not the geometry of the wing. So this side, the drag is a little more than on this side. So what it actually does is it turns the aircraft back towards the direction of the wind. So essentially, wing sweep back 2 is a stabilizing effect on the directional stability, just exactly like the fin. So there's another thing called side wash. There are three main contributions to side wash. Fuselage 2 acts like a lifting body. After all, you want to ensure the overall drag of the aircraft is low. So you're not going to have a very blunt and odd shaped fuselage. Generally, fuselage will be circular cross section with a conical end at the front and the back in a passenger aircraft, or as smooth and as smoothly cross section increasing fuselage in a combat airplane. So essentially, it's not a very good lifting body, but it still is a lifting body, which sees the yaw angle as an angle of attack for that particular lifting body, and it generates a certain amount of force. Another thing which happens, the wing flow over the wing is also asymmetric because of the side wash. Okay, the propeller, if there is a propeller in front of the aircraft, what the propeller does is, it produces a rotating wake. Okay, the propeller in the front has a wake which is airflow, which is rotating, which is in a kind of helical. It moves like that, and that causes a certain amount of asymmetry over the flow. This is, I'm talking about the tractor propellers, or the propellers in front of the aircraft. Now, some aircrafts have a propeller at the back. They are called pusher propellers. So they don't have much of an effect. And of course, this slipstream, it is called a slipstream of a propeller, doesn't have, is not there in a turbofan or a turbojet engines. The side force, unfortunately, cannot be computed easily and can be measured only if your the wind tunnel model is carefully designed. CFD is not very accurate in estimating side washes. So the next part we have to look is, we have looked at the stability. We also now have to look at the control. Okay, it's not enough if the aircraft is stable. It should be also controllable, because it's not all this going in one direction. You need to be able to move the aircraft in whatever direction, or the pilot needs to be able to move the aircraft in whatever direction he has to do, and to ensure he minimizes the drag, and of course, which directly leads to reduced fuel consumption and all kind of things. So in some cases, the rudder has to be deflected. Okay, we'll come to the specific cases later. Right now, we have to ensure what is the rudder power available. So what we mean by power is basically how much force can it produce, and what will be the resulting moment about the center of gravity. This should be large enough to maintain zero yaw under the most extreme conditions. Okay, so what we mean by most extreme conditions is, let's say the pilot is going to take off from the runway, and the runway is aligned in one direction, and there is suction in one direction. If the aircraft static stability ensures that it aligns itself towards the wind, then the pilot will not be able to take off, because he will go off the runway. So under such condition, the pilot should be able to deflect the rudder to counteract the incoming, what you can say, keep aligned with the runway. And there are other extreme conditions where the rudder should be able to handle, which will come subsequently. Okay, so the basic stability criteria, as we talked about earlier, in this case, if you plot the CN is the side lift coefficient, okay, side force coefficient, just like CL is for the lift, vertical lift coefficient, this CN is for side force. And with respect to beta, so what you see here is a positive line. Okay, CN beta is greater than 0. And this is a stabilizing aircraft. So airplane stability should have a side force as a beta plot, which has a positive slope. So which means that when the beta increases, the force produced should be in the positive direction and getting it back into this direction. So this has a little more detail in this figure. So what actually happens in this case, if the aircraft, for example, has yaw to the left, or the side force is ensuring that this angle of the flow is in this direction, you want it to go back towards that. So on this part, when the beta is increasing, the side force should be in this direction. When this side, where the slip angle is reducing, negative, then it should be in other directions. Essentially, this is just to show that this is a stabilizing force to be generated. Okay, now let's see a little more detail, yawing moment coefficient versus angle of yaw. Okay, so these coefficients, these are the points. For example, if you see in this case, the nose is pointing away from the wind direction, so it has to correct itself. CN beta slope is 0. If it is negative, CN beta is slope is negative, then this becomes unstable. Okay, and this is something which you should understand. This problem is not very prevalent among passenger aircraft, but it sometimes shows up in combat airplanes, largely because of the kind of tail volume ratios which are possible in combat aircraft, and also the extreme maneuvers the combat airplanes indulge in. So just to give you some numbers or ideas of different kinds of CN beta values. So from, let's say, from 0 to about 0.6, most of the aircraft they don't change. Okay, they are around here between 0.05 to 0.1. In case of F-104, this is an old fighter plane which was somewhere during Vietnam War, and that because of the fact that it was a supersonic aircraft, it would go into widely varying CN beta curves, including sometimes where it was becoming unstable. Okay, so this blue curve I have included for a specific reason. This part, right from about 0.2 to about 0.5, it has a positive slope, this curve. Then it shows a negative curve. So what is happening here in the transonic zone, it was becoming unstable in the directional stability. And now again, it back to stable. After that, again, it goes out into unstable. So they had to fix this later part. So there are some numbers target for for multi-engines. You need to have slightly higher CN beta. I'll come back to that. A single engine, a subsonic, these are the values. Why multi-engines could be a problem? Why you need a larger CN beta is if we have multiple engines in an aircraft, one of them could fail. So what happens when one engine fails in a multi-engine aircraft is that there is an imbalance in the thrust. First, the thrust is reduced, so you have to fly at a lower Mach number or a lower velocity to, because the thrust to overcome the drag is lower, you have to reduce the velocity. Second, if the engines are placed at a distance from each other, there is going to be a yawing moment produced by that. So that's the reason for multi-engines, you need slightly larger CN beta. We'll talk about that a little later to more detail. So summarizing what we are looking at is directional static stability is a measure of the aircraft's ability to realign itself the direction of the resultant wind. So this ensures if there is any disturbance due to side slip, this is effectively handled. So what we mean by effectively handled means that the aircraft is able to take care of without any pilot intervention. And the vertical tail or the fin is the main contributor for the directional static stability. So there are other secondary contributors like we talked about, the wing sweep, the dihedral and the side wash and the fuselage and other things, but these are secondary contributors. The main contribution is coming from the vertical fin. Okay, the other contribution, as I said, fuselage, wing, propeller and all that. DSS or the directional static stability is positive CN beta for positive beta. So remember this CN beta, the slope should be greater than 0 and CN should be 0 if beta is 0. Okay, I want to stress this point here. Remember in the, I think in the mock test I had given a CM versus CL equation where you had to have positive CM naught when the angle of attack was 0. Remember that? Okay. In this case, it's exactly the opposite, and the curve should actually pass through the origin. So when beta is 0, CN should be 0. The reason is we are in the symmetry plane of the aircraft. So most aircrafts are symmetric with respect to one plane. Okay, the left and the right half of the aircraft are symmetric generally, except in for example, when it's in a combat airplane or a bomber or something like that, or a missile or a bomb is ejected, or there is a drop tank which is dropped. Generally, it's not done that way, but it can happen that one side of the drop tank is dropped and the other side is there. So there is some kind of asymmetry. Right. So when the aircraft is symmetric, there is no side slip. There shouldn't be no side force generated. Okay, and we'll see that why this is so and what happens if this asymmetry is induced. And asymmetry can be induced because of several reasons. One, even if nothing falls off from the aircraft, if it's a multi-engine aircraft, one of the engines could conk off and then stop producing thrust, in which case there is a significant asymmetry which leads to the side force being generated, which has to be countered. So this is the first part. Now I'll go to the second part of the directional stability. The objectives are same, there is no thing. So there are some observations we need to start looking at here. And these observations are associated with yawing and rolling being cross-coupled. Okay, so any angular velocity in yaw unfortunately produces rolling moments, and any rolling moments produces yaw. These are coupled. So if the pilot steps on the rudder pedal, usually the rudder is operated by the leg, and the pilot steps on the rudder pedal, causing the aircraft to yaw. One wing will advance and the other will retreat. The faster moving will produce more lift than the other, which will cause, as I said, it will be a directionally stabilizing effect. More lift means more drag, so the aircraft will align itself to the direction which the wind is coming. That is only the drag part, but the lift is also larger on the wing which is advancing compared to the one which is retreating. Because of this, there is a rolling moment. So what is the stabilizing effect in terms of sweep back and other things or yawing is a destabilizing effect in the rolling motion. Okay, and of course this will be exaggerated if the wing diahead is also there. That's a little more complex flow field, but just remember what is a stabilizing increase in drag in terms of yaw produces a roll. Of course, during a normal flight, when the aircraft is flying level and straight, the symmetric motion, all lateral motion and force variables are zeros. So essentially, there is no trimming problem, okay, in terms of whether you want to deflect the aileron and rudder in normal flight. Okay, however, there is an unbalanced moment with respect to pitch. Elevator has to be deflected. So in the pitch condition, the elevator has to be deflected. The reason is for static stability, longitudinal static stability, we have ensured the lift vector, the resultant lift vector acts behind the center of gravity, giving it a nose down moment, which has to be balanced out by a nose up moment being generated by elevator. So while in even in level flight with no acceleration of any kind, elevator has to be deflected for trimming condition. There are no trim problems in terms of both roll and rudder, both roll and yaw. So lateral controls basically secondary trimming functions, and that happens in case of asymmetry. Okay, so and the other part is that effect of center of gravity, moment of center of gravity is very significant in terms of pitching of the aircraft, but not so significant in terms of directional stability or lateral stability, roll stability. The other observation is because of cross coupling, rolling motion will cause side slip and side slip will cause rolling motion. So these are two coupled. So we have to understand them, what the coupling means and how this can be handled. So let's look at the roll and yaw coupling. So if the aircraft tends to yaw, let's say the aircraft wants to turn left. The pilot wants to turn left because he has to move this aircraft in this direction. So what he does is he deflects the appropriate rudder. In this case, the rudder goes this way, side force is produced along this direction, and the aircraft starts to turn. When this turns, there is, as I said earlier, there's going to be change in lift and drag here, which is going to induce a roll. That was the part which we discussed. Now let's assume that the aircraft wants to roll left. If he wants to roll left, he's going to deflect this aileron down and this aileron up. Okay, so this lift in this direction is higher, so the aircraft will roll. So this also has a drag. When the aircraft wants to roll or turn in this direction, nose goes in the other direction. Okay, so this is not exactly what the pilot wants to do, and he has to correct it. So whenever you deflect the aileron or the rudder, you have to have the appropriate motion of the other component, because these two are coupled. So one way to address this adverse yaw is to try and eliminate the difference in drag when you deflect the aileron. Okay, remember, when you deflect the aileron up or down, profile drag does not change. In the normal aileron, what changes is the drag produced because of the down deflection of the aileron, which increases the lift, and lift induced drag is what increases. And this is what produces that adverse yaw. It also gives you a clue. Because the profile drag is same whether deflected upwards or downwards, is it possible for us to play with this factor? Can we deflect the ailerons in one way which has a higher profile drag than the other? So this is something which has been tried and it's called a freeze aileron. I'll show you a figure of how it operates. What really happens when the pilot wants to roll left in order to turn left? There is a yawing moment opposing this, and this is called the adverse yaw. And this, of course, is very pronounced in aircraft with large aspect ratio, especially passenger or cargo aircraft, because as you see, the ailerons are at the wing tips and the momentum is very large. When the momentum is large, the adverse yaw also is large. So as I said, the drag increase is because of induced drag in one side when the aileron is deflected down and not in the other. So one solution which was being tried is to ensure that the ailerons are not deflected symmetrically, in the sense that when they go up differently, and when they go down differently. So what you see here, for example, in the down deflection, the top surface of the wing with the aileron deflected is smooth, okay, and it's like a cambered wing. As long as the deflection is within 25 to 30 degrees, there is no flow separation at the top. The flow is smooth, flowing smoothly. So the profile drag is fairly under control. Now, what I'm trying to do here is, if I deflect the aileron upwards, what you see here is a severe discontinuity in the flow. Now, this causes a larger profile drag. Okay, so when the this one, the drag is increased because of induced drag, but the profile drag is not high. In this case, the profile drag increases on the other side of the wing to try and compensate for the increased drag because of induced drag here. So what you see here is the aileron is not hinged at this point, but hinged slightly differently. So this is one of the methods which has been tried to ensure that you don't get into adverse yaw scenarios. These are fixes which came later, but if you have designed the aircraft from the beginning reasonably well, you will not find too much of a adverse yaw. In fact, in the case of Tejas, this wasn't there. This was more a proverse yaw, in the sense if the aircraft, the pilot wants to turn left and rolls left, the yawing also is in the same direction. So it's called a proverse yaw, which is not very common, but it was found at least in the initial design stages of Tejas. So if the freeze aileron is designed properly, that can reduce or sometimes even eliminate the adverse yaw. Another way to eliminate adverse yaw is deflection of ailerons. Basically, the traditional ailerons, let's say you deflect 20 degrees on the right wing, 20 degrees up on the left wing. So you don't have to do that. So you can deflect 20 degrees down on one side and different angle on the other side. So this is also possible. So you deflect it at two different angles. So differential deflection means that the up aileron is deflected more. And if you deflect this more, the profile drag increases. Whereas in this case, the profile drag is not so high. It's always there because any object in a flow will have a profile drag and a skin friction drag and an induced drag. In this case, the induced drag is there, but the profile drag is low. In this case, the profile drag is higher. So these two, by differential deflection of ailerons too, you can try and address the problem of adverse yaw. Basically, the idea is to contract the play with the profile drag part of the total drag term to try and address this adverse issue. So in some cases, the roll control is also done by deflecting what are called spoilers. Okay, these spoilers are essentially a flat plate suddenly raised towards the direction of flow. They are only producing drag. They are drag producing object. They do not produce lift. So only the profile drag component is there. There is no induced drag component. So what happens in this case, as the figure shows you, this part of the wing, the profile drag is larger. Okay, and this part of the wing also the lift is reduced because you are disturbing the flow. Okay, so what happens when this happens? It creates a rolling motion. See, the lift is lower here, higher, so the aircraft turns in this direction. And because the drag is more here, the aircraft also goes into the same direction. It's a natural direction. Just to, as an analogy, just imagine you're riding a motorbike and you want to turn left. What normally motorbike drivers do is lean to the left and the aircraft automatically turns left. Just imagine you're driving a motorbike and you lean to the left and the motorbike goes in the other direction. That could be a catastrophe. So these spoilers are there in most passenger aircrafts. They don't, of course, always use it for this. Just when they are coming into land and they need small adjustments in terms of angle or roll or yaw angle or things, they use this small spoilers initially. And once they land, they want to ensure that the aircraft stays on ground. So basically, you're trying to kill the lift component as quickly as possible. So they deflect the spoilers on both sides of the wing so that there is a tremendous increase in drag and also tremendous reduction in lift because they kill the flow over the wing. So once the lift is reduced, the weight of the aircraft, larger and larger part of it is on the landing run, and the drag also is larger. So this is one way to brake. So just as a matter of sidebar here, when the aircraft touches the ground, just when it touches the ground, the lift is almost equal to weight, slightly less. So the reaction force from the landing gear on the wheels is very low. Okay, so how do you bring the aircraft to stop is to brake it. So what I mean by braking it is increasing the resistance of the aircraft to move forward. This could be either brakes on the wheels, just like we have in cars or motorbikes. But in aircraft case, because the velocities are very high, and if you jam the brakes on the landing gear, the aircraft will tip forward. Basically, it'll nose down and crash. Because the landing gear is below the center of gravity and you apply brakes there is a nose down movement and it will crash. So what pilots do is try and increase the drag, and since the wing is very close to the center of gravity, this increasing drag is like a aerodynamic braking and it doesn't even produce a nose down movement. Right. Another thing is it also has an additional effect of killing the lift, increasing the weight of the reaction force on the wheels. Now the friction drag which happens when you apply the brakes on the tires depends on the overall equivalent weight of the aircraft. When the aircraft is not moving, it's the total weight of the aircraft which is acting on the wheels. But when the aircraft is moving, there's a certain amount of lift being produced. So the weight on the wheels is less than the aircraft weight. Okay, so these spoilers are essentially used during landing and in rare occasions also to create some kind of proversia. So while yaw stability we have talked about, we also need to look at the yaw control. So what we mean by control is it's not enough if the aircraft is stable all the time. The pilot should be able to ensure that he's able to control the aircraft, meaning basically do whatever he wants to do or align the aircraft in whichever direction he wants to align. And this is achieved through deflection of the rudder. Okay, that's the only way he can do, or of course he can move around the ailerons a little bit, but major directional control is through rudder. So it's interesting for a designer or for an engineer to know what should be the angle of deflection of my rudder if I want to do certain things. Okay, so basically, if I want to yaw 5 degrees to the right, what should be my angle of deflection of the rudder? Basically, you are trying to find out delta in this case is rudder deflection angle, which of course in an all moving tail could be the whole movement of the tail. What is the increase I am getting in the side force coefficient for every 1 degree deflection of the angle? Now this basically depends on the vertical tail volume ratio and the lift coefficient produced by the not the wing but the vertical fin. So why is this critical component? This is critical component because the aircraft has to maintain zero yaw in some extreme flight conditions. Okay, these are eventualities which the pilot should be able to counteract. Okay, and as a designer, again, you need to ensure what should be the actuator or what should be the jack which I need to be able to use or design or put there so that the pilot is able to move the rudder to the desired angle. This used to be initially interesting or crucial in the early days when the rudder or all control surfaces were connected to the pilot through cables and pulleys. So if the hinge moment is too high, the pilot could not deflect the rudder. So because of that, there are ways to calculate it. Even now it's needed to calculate, but now with all this hydraulics and fly-by-wire and very high-speed actuators and all that, it's not such an important thing, but it anyway computed. And it to be needed because finally, to move a control surface, you need a jack or an actuator. And somebody has to say what size of the actuator I need, what load carrying capacity I need. Correct? For example, if you want to lift up a car, you need to have the appropriate jack. You cannot use a car jack on a lorry to lift the lorry. So that jack is essentially to apply the force needed to move the rudder. Why you need a force to move the rudder? Because the aircraft is flying and there is an enormous amount of force being generated by the wind movement. And because of that, it's very difficult to open move the rudder in either direction. You have to oppose the drag. Okay, so you can experience this. If your car is static, it's easy to open the door. If the car is moving at a fair enough speed, you'll see that you need to have a larger force to even open the car door. That's because of the force being generated because of the airflow. So in some combat airplanes, it's kind of becoming popular, what are called all moving fin. And this is necessitated by the fact that the original rudder size was not enough for it to be able to produce the necessary yawing moment needed to counteract whatever is the disadvantaged flow. So the advantage of this is that you have a larger area for you to deflect. A larger area means you need to deflect it at a lower angle. So lower angle means the danger of stalling. Finally, it's an airfoil section. If you tilt it at a very high angle of attack, it will stall. Just like the wing, the tail also will stall. And tail stalling is catastrophic. So I want to stay within the beta angle, which is linear and which is much below well below the stall angle. So one way to do that is to reduce my CN, basically side force coefficient, and that can happen if I increase the area. All aerodynamic forces are dynamic pressure times the lift, the force coefficient times the area. So if I have a slightly higher area, maybe I can deflect the rudder little less and have a better control. And this is very useful in the case of combat aircraft. And because, as it is, as I said earlier, the combat aircraft moment arm is smaller. So we need a larger area. And sometimes the vertical tail area is required is so high that you cannot have a single vertical tail. You have two vertical tails placed at a slight distance between each other. And for example, you can see that in some of the most modern combat airplanes. And in some airplanes, not only they are two vertical tails, they're also canted at an angle. When I say canted, it's not like this, it's at an angle. So that's essentially to reduce the interaction between two vertical tails, because after all, they are two lifting bodies and the flow between them can be, there will be interference between that. Other thing is to try and reduce the radar reflection in case of enemy radar eliminating you. So that's now the all moving fin, as I said, has come into prominence because of that. Now we talked about control. Control means being able to produce the force and moment as desired by the pilot, and which means that I need to find out the size of the rudder. What should be the area of the rudder, or how far should it be from the center of gravity? Essentially deciding on the sizing. Okay, see, finally this aircraft has to be manufactured or fabricated in the factory, which means that you have to tell them what should be the aspect ratio, what should be the root card, what should be the tip card, what should be the type of airfoil used. Rudders, of course, are always symmetric airfoils, and all kinds of things. So basically, you need to be able to design the rudder, which means you have to size it. How big should it be? And in the normal flight conditions, of course, you don't need the rudder at all because the aircraft is symmetric and you don't need to deflect either the rudder or anything. But it's not the normal conditions you're flying all the time. You need to be able to reorient the aircraft in whichever direction you want. On top of that, you also need to be able to counteract certain adverse conditions. Okay, and they should have certain control authority. Basically, control authority means you should be able to produce the required moment, and to produce that moment, you should have the momentum as well as the force. So some of this we'll discuss now. What are the critical conditions for which the rudder is designed? First, look at the crosswind. Let's say the pilot is coming in to land, and there is a very strong crosswind blowing. And when the crosswind blows, this is going to produce a side slip, and the static stability of the aircraft ensures that it realigns in the direction of the wind flow. Okay, this is what the positive direction stability, whatever we have designed or built into the aircraft, will ensure that it will turn itself towards the direction of the wind. But this, of course, is not welcome, especially during takeoff or during landing, because the aircraft has to be, of necessity, be aligned towards the runway. Right? You cannot automatically align to whichever direction the wind is flowing. You need to be aligned towards the runway. So which means the aircraft should be able to produce an opposing force and an opposing moment to counteract this yawing produced by crosswinds. So the regulations say that there is a limit to which the pilot can counteract this. So if the crosswind is coming at a certain angle beta, at a certain velocity v, only up to that the pilot will be able to land. So if it is more than that, the pilot will have to ditch the landing and go into another airport. If he is in the takeoff mode, of course, he can abort the takeoff and return back to the bay. So you cannot have very, very high beta angle and side slip angle and all that. Also, we cannot have a very high gusty winds. There are cases where this can happen and the aircraft will find an alternate runway, alternate airport. One thing which happens, especially during takeoff, is when there is a side wind, the pilot has to necessarily deflect the rudder to counteract that. So what happens if we deflect the rudder? It increases the overall drag of the aircraft. So the takeoff performance will be below par. So if the side slip forces, the side wind is too large, the runway may not be enough for the aircraft to take off. So that's another danger. But if the runway is long enough, performance is lowered, but still you'll be able to take off and complete the mission. So this is just pictorial representation. The runway direction is in this dotted direction, but the wind is coming here. This part of the aircraft looks like an airfoil. As I said, after all, it's a symmetric body, streamlined body, and it's at an angle of attack. This produces a force called LF here. Okay. Now this force will automatically align it towards the direction of the wind, whereas the runway is in this direction. So how do I counteract that? I deflect the rudder in this direction as shown here to produce a force opposing this LF, so that the total force, what produced by the rudder and produced by the beta, is equal to 0, and the aircraft continues to be aligned in the direction of the runway. Okay, now if this beta is too high or V is too high, you do not have enough rudder control to align yourself to the runway, then the pilot aborts the runway and returns to bay. Okay, or if he is coming into land and these two conditions are larger than what it is designed for, the pilot of necessity has to abort the landing and go find another airport. Okay, this is an interesting thing happened recently. I believe you all read that about 4 or 5 days back or a week back, there was a crash of Airbus, which happened in, I think, I'm not sure whether Karachi, I think it's near Karachi. It was suspected that one of the engines failed, and the pilot could not land properly. There's still an investigation going on. It's not clear whether the crash, nearly 100 people died, was because of one engine failure and the pilot being unable to control, or something else happened. So anyway, all aircraft are designed for a condition if you have multiple engines, meaning more than one. Combat airplanes, this is not an issue because combat airplanes, usually they have only one engine. In some cases, they are twin engines, but even if they are twin, they are very close to the center line. For example, F-14 has two engines, but they are stuck together in the fuselage. So is Rafale. Tejas has only one engine. It's almost aligned with the center line. So one engine failure anyway, it's a catastrophe. Rudder or anything, nobody can do anything. But if you have two engines like an Airbus or a Boeing or a passenger plane like that, one of the engine fails, then there is going to be a severe yawing moment, and that has to be handled. Okay, so as I said, the recent crash in Karachi, in some cases they say that the pilot's voice says engine has failed, but one engine failure, definitely the rudder is designed to take that. I mean, that is a condition in which it's designed. So if the engine fails, there is a severe yawing moment induced, and the rudder should be able to counteract this side slip. Okay, if the rudder authority is not enough, or the force being produced by the rudder is not enough, then the aircraft will go into catastrophic control. And then once it starts yawing, it will roll and the whole thing will go out of control. So the rudder must be designed to have sufficient control authority to handle such conditions. One engine failure condition should be anticipated. So if there are, let's say, more than two engines, let's say there are four engines, some older aircraft had four, you have to assume that the farthest engine from the center line, fuselage center line, is the one which fails. This is the worst case scenario. Okay, so when I say control authority, I mean its rudder should be large enough and has adequate momentum both to generate the force needed to overcome this. So this is a condition which has happened many times. So engine failures happen, the pilots have come back and landed. The performance, of course, will not be anticipated. He has to fly a lower velocity, reduce thrust and all that. But it doesn't normally lead to any kind of crash because the rudder design, if it has been done well, I'm sure Airbus has done that correctly, it should not cause any problem. There's another scenario called rudder lock. And this is mostly with respect to combat airplanes. When the airplane goes into very, very crucial or critical or extreme severe maneuvers, then it's possible the aircraft is yawed into a very high angle of yaw. Okay, and especially when he's trying to do a very high side slip. Okay, when in this case the angle of attack, yaw in this case is so high, and if the vertical tail is kind of designed not well, it has a large aspect ratio but small area, it may stall. So what happens if the vertical tail stalls or horizontal tail stalls? As I said earlier, tail stall is to be avoided at all costs. So once the vertical tail stalls, there will be a drop or almost zeroing of directional stability. So once the aircraft has gone into side slip, let's say pilot induced side slip or any other arbitrary side slip happens, and the only way to recover is for the pilot to deflect the rudder. Okay, but if the rudder has stalled, then he is not able to control it. And the stall may be enough for him not to be able to generate the force needed to for the aircraft to be brought back under control. So, okay, let's spend a little more time on this. See, the side loading resulting from yaw will tend to force the rudder on one side. Okay, it's like, if your airflow is there, the rudder automatically aligns itself in the direction of the flow. And once it is already there, or if the pilot has put it in that direction, in that deflected zone for this condition, and it stalls. If this happens, the pilot is not able to apply enough force. The pilot, or even in the fly-by-wire case like an Airbus or any other modern combat airplanes, there is not enough control authority in the rudder for it to get out of the stalled condition. See, only way to reduce a stall, recover from a stall, is to reduce the angle of attack. Angle of attack in a pitch, or angle of attack, angle of yaw in yawing conditions. Okay, why does the aircraft stall? Because the flow over the wing or the flow over the vertical fin separates, and this separation happens at high angles of attack or high angle of attack. So only way to recover is to try and reduce that. Okay, if it has gone into a severe side slip maneuver and the pilot wants to reduce it, but because of that maneuver he has gone into, the rudder is locked and he's not able to deflect it because of the force. Earlier, aircraft, the pilot was connected, as I said, to the rudder with cables, and they had to use their leg to move the rudder. And under lock condition, they just could not move it. So that's how the name came in, rudder lock. Okay, it means that there is still there is no effectivity of the rudder, and the pilot is not able to recover from the side slip condition, and it is going to crash. Okay, so this problem has been resolved by what's called a small dorsal fin. Remember, I showed you a figure with the C and beta curve with two curves, one with and without dorsal fin. So we are going to talk about what a dorsal fin is now. So dorsal fin is a small surface, as you see here. This is the vertical fin, and there is a small extension. What you see here, the yellow part. Okay, and one thing I want you to observe is the vertical fin has a sweep angle, which is this, but the dorsal fin sweep angle is much larger. Okay, larger sweep angle for the dorsal fin, and it's not extending all the way. It's only the route for about, let's say, 10 to 20% of the span of the airfoil, the vertical fin. It could, of course, be a very simple plate that will do the job too. But having put something there, you want to have a minimal drag, so you have a nice curved shape, or even you can optimize the shape so that it merges here smoothly rather than the sharp corner here. So what it is doing is it's like equivalent to having two sections of the wing, one with a very high sweep angle and one with a less sweep angle. Okay, high sweep angle means that the flow, automatically the flow over the wing is seeing a reduced normal component. Remember, the sweep reduces the normal component of the wing. That's why you use highly swept wings at high Mach number conditions. So low normal flow means that the probability of it stalling is lesser. So it can take higher angles of attack than normal low sweep angle. So that's one of the reasons the delta winged aircraft can operate at much higher angles of attack than normal wings because of the very high sweep angle. So the advantage we see here is because this is a higher sweep angle, while the vertical fin may have stalled in that condition, but this fin will not stall. So that's the idea of putting a fin there. A small dorsal aspect ratio dorsal wing, also larger sweep, will not stall, whereas a small the larger aspect ratio fin will stall. So a smaller one will remain unstalled at even high angles of angle of yaw, because smaller aspect ratio surfaces stall at a higher angle than larger aspect ratio and the sweep angle. So this helps maintain a sufficient directional stability up to a higher angle of yaw, rather than it's not without limits, but it does improve the side slip angle where you can control it. So in the absence of the dorsal, the entire tail would have been stalled, but because of the dorsal, part of the tail is stalled, part of the tail is not. Okay, I'll show you in the next figure. So what the high angle of high sweep angle dorsal fin does is it will produce a vortex. Okay, the stronger, the larger the sweep angle, the stronger the vortex it generates. And that is something which is an understood fact. And what you can see here in the next fin, this is the dorsal fin, kind of close-up of that picture. Let's assume that the vertical fin is already stalled, as indicated by this random movement of arrows. The top half of the vertical fin is stalled. Okay, there is this is not stalled, and the discontinuity here, leading edge discontinuity, creates a vortex. Also, vortex coming in from this continuity. So these two ensure vortex is kind of mixes the flow, high energy flow and low energy flow in this plane, and ensures that this part is only partially stalled, not fully stalled. This part is fully stalled, and this part is only partially stalled. So there still is some control authority with respect to the rudder, which the pilot can use to recover. So this allows the CN beta to be maintained slightly better at higher angle of yaw, and also helps in things. One other thing it does is if you have a slightly higher aspect ratio wing, which has a tendency to flutter because of aerosity, and you have strengthened it by putting a slightly higher root section here. So it has multiple benefits, and it has been used extensively in most of the modern day aircraft which have this kind of fin. So what does it do essentially? I'll come back to the same figure here. So you can see without the dorsal fin, you would have had a slight change in CN beta. Eventually it would have come the other direction. Remember, you need to have positive slope, and it's becoming 0 here and then going down at 25 degrees. Now with the dorsal fin, you're still able to go at a higher CN beta. You can have a higher correcting force. So essentially dorsal fin augments the directional stability of an aircraft, and it has been used in many combat airplanes and not so much in passenger planes. However, in passenger planes you may still have some small part of it that is mostly to blend the fuselage and the vertical plane smoothly, rather than any CN beta effect needed for them. Okay, but you don't normally want to have sharp corners, so you blend it smoothly. You'll see that in many of these aircraft you have that. In Tejas you see something like this, but that's not exactly a dorsal fin. It's an environmental control system inlet for that. Okay, summarizing the directional static stability, what you see here is that these two are coupled. Directional roll motions are coupled. I'll talk about the roll motion in the next session. Directional stability is displayed around the vertical axis and depends to a great extent on the quality of the lateral stability. Directional stability is a measure of the aircraft's resistance to slipping. What I mean by slipping is the aircraft moving sidewards. So if the aircraft starts moving sidewards, because of the large frontal area produced here, the drag is very, very high, and that is not acceptable, except in some few maneuvers done by combat airplane pilots to reduce their altitude. Okay, again, going back to this case, what happened, unfortunate case where nearly 100 people died in an aircraft crash in Karachi. The pilot's voice recording says that the one engine failure has happened. The air traffic controller's voice is telling him that you are coming in at too high an altitude. Altitude is too high, the glide angle is too steep, and other pictures which people have taken have shown that the landing gear is only partially deployed. Okay, so it's not clear what exactly led to that crash, and it's very, very important that this is understood, because people's lives are involved and you don't want that to happen again and again. And if there's a defect in the design of the aircraft, needs to be addressed. Exactly just like there was a defect in that Boeing NG, 777NG, which led to 3 crashes. We need to figure out what exactly happened here. Directional stability is ensured by putting a vertical stabilizer or a fin to the rear of the center of gravity on the upper portion of the tail. This is again for conventional aircraft. Okay,